Hey people, in this video we're going to be talking about impulse and momentum. So let's get started here. I want to begin with what we might call a motivation for defining momentum and impulse. And so I think the best thing to do is to start with Newton's second law. So let me just put that down here. Remember, of course, that it's F equals ma. And just because I know I've been maybe a little bit fast and loose with this, it's one of the many things I've been fast and loose with. But remember that this is the net force on an object, right? And it's a vector. I'm not writing the sigma because it gets a little cumbersome, but this is a pretty standard notation. So I felt like I should just point that out. But anyway, let's think about the one-dimensional case here. And so we don't have to really worry about vector notation. And so this says, and I'm just choosing the x direction for definiteness, that the net force in the x direction is given by the mass times the acceleration in the x direction, right? And so we want to remember, well, let me put this in the document, that acceleration is the time derivative of velocity, right? And so with a slight abuse of notation, again, this is another one of those things that would make the mathematicians angry, we can write something like this. So nothing changes about Newton's second law except for now we're just going to write the acceleration as, a change in velocity, right? And I'm being specific about the x velocity here over a time interval, right? And we can rearrange this. So let's bring the delta t to the left-hand side here, and we find m times delta v sub x on the right-hand side. And the last thing I want to do is just remind you that this delta notation, we've been using it a ton, so probably everybody knows by now, but is just going to be given by, well, let me do it like this. V minus V initial. And then finally, we can just distribute out the wow, what are we distributing? I always use that word. Now I don't really think I know what it means. I think we're distributing the m, though. Yeah, that's what we're doing. Okay. I'm learning a lot teaching this class, I gotta say. So this, okay, and you might be like wondering, well, like, what's the point of all this? And that's a great question to ask. That sounded very existential, but I just want to write this in vector form, and then I think you'll see where I'm going with this. But so let me just finally say that generalizing this to the three-dimensional case, we can write, and now I'm going to go back to the vector notation. I'm going to write f delta t, and this is now a vector, equals mv minus mv naught, and I need to make these both vectors too, these v's here. And this actually, right here, what I've written is the impulse momentum theorem, but I don't want to get too ahead of myself. I want to first talk about momentum, and then we'll come back to what the impulse momentum theorem says. And so with this result here, right, which as I've said is the impulse momentum theorem, it kind of makes sense maybe to define a quantity that's given by the mass of an object, which is a scalar, of course, right, times its velocity. And so that quantity is called linear momentum. And let me just write linear here because we will talk about angular momentum in a little bit. Not in this video, but probably in a few down the line. So anyway, we define the linear momentum of an object with, how do I say this, of an object with mass m, traveling, I use this word a lot, at, or I should say with, sorry, with velocity v, to b, and this is momentum, right? I just said this, I haven't written the equation out yet, but I think we all see by now that it's just the mass times the velocity vector. And this is clearly a vector, right? So let me say this is clearly a vector because we know from our discussion in the very first lecture, right, about some of the operations we can do with vectors and scalars is that multiplying a vector by a scalar just gives us a different vector. Like really what it comes down to is it kind of scales the vector, right? Makes it longer or shorter. And this is an important property of momentum, right? That it's a vector, as is, well, this is something we want to think about for all the quantities we discuss in this class. But anyway, I'm just going to show you what the dimensions of this work out to be. We're going to have a mass, right, times a length over a time. And that's it. And the corresponding units, right, we always want to be thinking about dimensions in units, are then, and I think we all see this, but it's kilogram meters per second, like that. Okay. And I don't think there's a name for this. Not that I'm aware of. It's just kilogram meters per second. And so that's it, right? That's really it for momentum. I mean, we're definitely going to talk more about it and work some examples, but it's just the mass times the velocity vector. Incidentally, right? This means that we can write Newton's second law as, and we could simply write it as, and make these into vectors, but the net force is just the time derivative of the, of the momentum, right? Remember the dot notation, I'm going to stick a dot over this thing. And I believe that this is actually how Newton first expressed his second law himself, so I don't know. That's kind of cool, I guess. And if you were to take the time derivative of this, right, remember the mass is a constant, and so that doesn't get touched by the operation of taking a derivative. It just is a constant, and it can go out in front. But then when you take the derivative of the velocity, that gives you the acceleration, right? So anyway, let's look at an example of this, right? So let's say an object of mass m is 1 kilogram, is traveling in a straight line, and has a constant kinetic energy of 50 joules. What is the magnitude of this object's momentum? And you might be thinking, well, let me just solve for the velocity directly and then use that to calculate the momentum, and that's fine, of course, but I just want to show you this nice relationship between kinetic energy and momentum. So let's recall the definition of kinetic energy, and it's just K is 1/2 mv squared, right? And so we're going to tamper with it a little bit algebraically. And it's okay if you would never have thought to do this, right? Because this is a little bit weird, but you can just see this done once and then use this result if you ever need to. But I'm going to rewrite this as K is 1/2 times 1/m, and then times mv. This should be quantity squared, like that, right? And so if you were to expand this out, you would see that this is the same thing, right? Because you have the 1/2, you have the 1 over m that cancels out the m squared that you get from squaring that whole term inside the second set of parentheses, and then you're just left with 1/2 mv squared, right? And so this works out to be simply p squared over 2m. And therefore, we can say that the momentum is given in terms of the kinetic energy and the mass by, well, p squared, right? We just multiply both sides by 2m. And then we just take the square root of both sides, because what we want is the momentum, right? And so this is just p equals the square root of 2mk. And I don't have to use the approximately equal to symbol, because this works out to be a very nice 10 kilogram meters per second with no decimal places required. And so that's just, I mean, like, the thing is, like, I was, if I'm being honest, I was struggling a little bit of an example to do with the information that we just have so far. And I think that I would hope that applying the definition of momentum isn't anything that's going to be too tricky, because it is just, taking the velocity vector, however you want to express it, right, as, maybe an ordered pair or unit vectors or a column vector, it doesn't matter, and just multiplying that by a mass. And that's really all that goes into it. But we will, definitely do more with this idea of momentum in a little bit here. And so what I want to say is we can define the other part of the impulse momentum theorem. Now remember, the impulse momentum theorem is this thing, right? And we could actually write this one more time. Now that we have this definition of momentum, we could write this as delta p. And so, just to remind you, impulse momentum theorem is this thing. And so anyway, let's come back to what we were saying. The other part of the impulse momentum theorem equation, I guess, as the impulse, and this is usually represented with an I or a J, a capital I or J. And in the case of a non-constant force, we have to define this via an integral like this. And this is something that I just feel that I should mention, but isn't, something that we'll really be using in practice. But this is the most general definition, because this accounts for time-varying forces, right? But this is what this looks like. However, for a constant force, and we'll mostly limit our attention here to constant forces, I would say almost exclusively limit our attention to constant forces, we can write that J is just F delta T. And the last thing I want to say about this is probably kind of important, and this comes back to our discussion from the problem-solving session, right, about average values and integrals and whatnot. I think I did a decent job of explaining that in that video, so I'm not going to run through that again. But let me just say, from the discussion on calculating average values, of functions using integration, we also have that if we know what the well, so say the force is not constant, but we know what its average value is, right? Then we can write this. And so again, this is a vector, right? This is a vector, and what I want to do is put a bar over it to just indicate that we are talking about the average value here. And so this is fine if we know the average value of the force, even if it's, you know, not constant. Okay, and as I just said, this quantity, right, the impulse, is clearly a vector because of how we defined it, right? It's just the change in the momentum of an object, and if momentum is a vector, which it is, then change in momentum is also a vector, right? And so let's talk about the dimensions. And actually, maybe you all realize this already, but obviously it should have the same dimensions as momentum, right? But we can still do this because we don't get to the same dimensions in the same exact way. So we have that it is a force, or I should say a magnitude of force times a time interval, right? And then a mass times an acceleration times a time interval. And this is then a mass times a length over a time squared times a time, and we find the same thing as before, right? That it's a mass times a length over a time. And this implies, right, that the units are also then the same as for momentum, and they're just kilogram meters per second. I don't like how it capitalizes that. Okay, and corresponding units, and then let's just get this in here. Okay, so I think that's it for now, at least for defining some of the ideas and quantities that we are going to be working with here. So let's look at an example of applying the impulse momentum theorem. And what I want to do in this particular example is compare the result that we get to the result that we would get from applying the work energy theorem. And, you know, we should find, right, that we get the same result. And indeed we will. So let's do this. Well, let me read the problem statement first. Okay, so we always forget to do that, right? You push a box of mass m equals 20 kilograms resting on a flat frictionless surface with a horizontal force of magnitude F equals 100 newtons for delta t equals 5 seconds. Part A, compute the impulse on the box. Part B, compute the change in velocity via the work energy theorem. Okay, so the magnitude of the impulse is just J, right? What we call it, which is equal to the force times the time interval. And this, you know, I think we should just find to be 500 Newton seconds. Well, that's another way of expressing this unit, I suppose, is Newton seconds, right? So we see that Newton seconds are equal to kilogram meters per second. Same thing. But still, there's no, you know, one unit that I'm aware of, at least, that we can combine these into. Okay, go away. To get, you know, one unit that describes impulse or momentum. Okay, anyway. So we can equate this to the change in momentum, right? That's just what the impulse momentum theorem says. So the change in momentum is, and we're going to write F delta T equals delta P. And notice that this is probably clear, but this is a one-dimensional problem, so I'm not, writing these as vectors because we can simply indicate their direction with the appropriate sign, SIGN, and you probably realize this, but I'm imagining that the box is being pushed, say, to the right in the x direction, in case that wasn't clear or obvious. So, change in momentum, right, if the box is initially at rest, as we said in the problem statement, is the final momentum minus the initial momentum, and that's just mv minus 0, right? And from this, we go through, we solve for v. We weren't asked to do this, right? I didn't put it in the problem statement, but I'm doing it because we want to use it in the next part. We find that v is just f delta t over m, okay? So we'll come back to that. Now, for this part, we have to calculate something. We have to do kind of an intermediate step, and we can use, let me say this, we can use the equation x of t equals x naught plus v naught t plus 1/2 a t squared, right? This is from kinematics. It's one of the first equations I think we arrived at. And the fact that rearranging Newton's second law, we find that the acceleration is just the force divided by the mass, right? To write here, wow. Okay, I'm saying that the displacement here, or the distance, which is the magnitude of displacement, is just lowercase d, and so that is given by, if we take the starting position of the box to be at our x equals 0 position, which is, I think, the most sensible thing to do, we can write this: 1/2 a delta t squared. So we substitute for a, right? We just mentioned that the acceleration is the force over the mass, and delta t squared, that just stays what it is. We know what delta t is from the problem statement. And so we'll clean this up a little bit, and we find that this is f delta t squared over 2m, okay? So that's cool. Now we want to, I forgot what we were doing for a second there. We want to calculate the work that you do on the box, right? So the work that you do on the box, which is also, in this case, the net work on the box, right? Because there's no friction, just to stimulate your thinking about work, right? Because that's still a topic that you have yet to be tested on. And I'm going to say, which is also the network, and this is, we don't have to worry about the cosine or breaking the force or anything like that into its components, because, as I said before, we're imagining that this is all basically happening in the positive x direction. So we write this out, and we have the force. We just found the distance to be this, so I'll just copy and paste this here. And this works out to be upon, just combining everything, it just is f squared delta t squared over 2m. And remember that this is from the work energy theorem, right? This is the changing kinetic energy, and if it starts at rest, we just have that the changing kinetic energy is equal to the final kinetic energy. which is 1/2 mv squared. So I'm just going to put minus 0 here. Now, I'm not going to do the algebra here, but I would suggest that you do, just to make sure that I'm not lying to you. And you should find that the velocity is given by F delta t over m. And note that that's what we found here, right? So that's good. It's always nice to find that physics is self-consistent. So cool. And yeah, you can calculate the number, of course, if you want. I will not do that though. Okay, so hopefully this convinces you that in as much as like the work energy theorem is useful, the impulse momentum theorem is also useful, right? So let's talk about some of the implications of this thing, right, that we call the impulse momentum theorem. And I want to say that this, in the absence of external forces, implies conservation of momentum, right? It implies that momentum is a conserved quantity. So let me just say in the document here, notice that when and F is 0, this is the 0 vector, the impulse momentum theorem becomes, and I'm going to write 0 times delta t, this is still a vector, as strange as that is to say, and we have, these are vectors, right? And this implies that delta p equals 0. And this is really where we're going to get the most value out of these ideas, right, about impulse and momentum, is from conservation of momentum. And we'll look at a couple examples of this, and you'll do more practice problems on your homework. I don't know if I should call them practice problems, but you'll have more practice with this on the homework, of course. And I think that tomorrow at some point I'll probably also do another video where I just solve problems involving impulse and momentum. So this means that we can say, and I want to put this in a box when I'm done. You might be wondering, what's in the box? All right, if anybody gets that reference, let me know. Okay, so in the absence of external forces, the momentum of a system is conserved. Writing it symbolically, we can say for a given system something like this, and I'm gonna use the z direction here as well, even though we probably won't ever do that. But we do, you know, as I keep saying, right, we do live in a three-dimensional world, so it shouldn't be too shocking. And here I'm just writing this as an ordered triple. I'm saying my initial momentum is a vector with these components, right? P naught x, P naught y, and P naught z. And then when we are allowed to apply conservation of momentum, this means that we can write the final momentum like this, just without the 0 in the subscript. Cannot speak tonight. And this is conservation of momentum, right? In a nutshell. And so I promised I would put this in a box. So this is important. This is probably the most important thing that we've discussed so far. And notice how that just fell kind of nicely about looking at the from looking at the impulse momentum theorem and saying, well, what if the net force is 0, right? And that is the net force on an object is given by the external forces on the object, in case I need to say that, right? We're probably all comfortable with that idea by now, but anyway. Okay, so that's it, right, for conservation of momentum. I want to talk about collisions now, and I probably should have said this when we were talking about kinematics, but better late than never. I'm going to say a collision is simply when two objects are in the same, or I should say at the same position at the same time. And so symbolically, if, let's say, R of t is the position of mass big M, and little r of t is the position of another mass, little m, to indicate that they collide with each other at some time, some specific time. I'll call it t star, I suppose. Actually, I really don't like that because that makes it seem like the complex conjugate of t. Okay, so let's call it t naught. We write r of t naught equals r of t naught. And there you go, we have a collision. Right? It's exciting stuff. And you know, the funny thing is that many of you are probably watching this right now and being like, well, of course I know this. This is common sense, and I would agree with you, but you would be surprised at the number of times I've seen students forget this thing when in the heat of the moment, right? Okay, I don't like I shouldn't even say this, but I'm going to. I think there was like an exam a little while back for one of the classes I was TAing for where somebody well, okay, so the instructor asked, like, it was like two people running on a track, and it was like, you know, at what time and position do they pass each other? And one of the students wrote that the positions for each of them were different when they passed each other, right? Like, you know, and I mean, it's the easiest thing to do when you're caught up in all the math and stuff, but I just want to make this clear, I guess. And anyway, there are different types of collisions, right? So let's first talk about a perfectly elastic collision. And this is a collision in which there is no loss of kinetic energy during the collision. And so for a perfectly elastic collision, then we have delta K equals 0 and delta P equals 0. And this is the perfectly elastic case, okay? And let's think of a real world example, right? And so the first one that comes to my mind, let me just write this in the document, a typical example of this would be two rigid bodies colliding on, you can think about billiards balls. You know, it's a funny thing, like I would never in everyday speech say billiards, I would say pool, but all the textbooks say billiards, so I'm gonna say that too. But anyway, imagine that you're shooting pool, right, and you hit the 8-ball, say with a cue ball or something. The pool balls, they're pretty dense and made of hard wood, right? And so let me write this. The shape of the balls deforms very little, if at all, when they strike each other. And so no energy goes into the deformation of their bodies, right? And you could contrast this maybe to say like a tennis ball, right? If you've ever seen somebody hit a tennis ball in slow motion, the ball very much flattens out, and you can bet that some of the energy in that occurrence goes into just flattening the ball out, right? Just changing its shape and not, its velocity. So that's that. And I mean, pool balls even, right? They would still probably deform a little, probably compress a little bit upon colliding, but it's not anywhere near how much like a tennis ball might, or some other kind of ball. Okay. So that's a perfectly elastic collision. Momentum is conserved and no kinetic energy is lost. So we could say kinetic energy is conserved as well. And let's talk about now an inelastic collision. Is a collision in which the kinetic energy does change, and I would say, and it usually decreases. I'm having a hard time thinking of an example where it would increase. And so we can write here, to just kind of summarize this in equation form, that delta K is now not equal to 0, but delta P is, right? And this is inelastic. Now, we will look at one more type of collision, which is really sort of just a subtype of inelastic collisions. But you'll see, right, that in essentially all the collisions that we think about, momentum is conserved. And so I would say, just as a practical matter, right, for strategizing, if you're looking at a problem and you're not sure whether to use conservation of energy or conservation of momentum, know that based on this, right, it seems like conservation of momentum is a little bit more general and likely to apply. And I think that is a good thing to keep in mind. So let me actually just give you an example of an inelastic collision. This is going to be kind of gruesome, but an example of an inelastic collision. Could be a car accident, right? Where a certain amount of energy is lost in the process of deforming, let's say, like the frames of the car, and as heat, maybe. So it obviously is going to take energy to like bend, let's say, steel, right? And so that's, this is kind of a dramatic example, but hopefully it gets the point across, as dramatic examples I think usually do. And so the last one is going to be, like I said, a subcategory of just a regular inelastic collision, and this is called a perfectly inelastic collision. There we go. And this is a collision in which the maximum amount of kinetic energy is lost. And so here, the colliding masses stick together and move as one object after the collision. And so for those of you who are sports fans out there, an example of this could be, I don't know, during a baseball game, when the forward from one team tackles the point guard from the other, right? And there are more examples than this. We'll actually look at an example. I made a problem up in this. This problem right here, this example 11.3, is actually going to be a perfectly inelastic collision. So if you're not into sports, you can just follow along with this and kind of see what the idea is. So this example, 11.3, let's talk about it. You throw a lump of clay with mass of 0.5 kilogram at a box with mass 10 kilograms such that the lump of clay has a velocity with x component v sub x equals 10 meters per second right before it collides with and sticks to the box. What is the resulting speed of the block clay system after the collision? So what we want to think about, and I actually... we'll make a sketch here. I have a Zoom meeting open with myself, just so I can use the tablet on the whiteboard here. So let me just make a sketch of this, right? Because I think that's going to be useful. And so when we're thinking about the initial momentum, the setup is going to look like this. We have, say, a box just sitting here on the ground, and this is my lump of clay, and we're thinking about the time when the box is at rest, but the clay, say, has an x component of velocity v sub x is what we called it, right? And we're not, you know, I wanted to look at some simple one-dimensional examples before we work on two-dimensional examples, and so we're kind of just ignoring what's happening in the y direction. You know, it's probably not really possible to throw a lump of clay at a box so that it only has an x component of velocity, but let's just pretend that we can for the time being. I mean, we can certainly throw it so that it has like a negligible y component of velocity, and that's, I think, what I want to think about here. So this has mass little m, this has mass big M, and this is at rest, right? I don't know how I want to indicate that in the diagram here, but the block is at rest, so the only thing that's moving at this time is the lump of clay, okay? But now, when we're looking at the final momentum, now the clay is stuck to the box, right? And they're moving together, and I think I called this, let's say that now the mass of this object, this is our system, right? The block clay system has a mass of big M plus little m, and is moving with a velocity in the x direction, and this is supposed to be a big V. You can't probably tell when I write it with the stylus, but you'll see that when I type it up. But this is the picture of what's happening, right? And it's useful to make a sketch and think about what this looks like. And so with that out of the way, I'll come back to actually solving the problem here. So the initial momentum of the system before, let's say right before, right? We're thinking about like the clay being, you know, maybe millimeters away from the side of the box. So we'll say the initial momentum of the system right before the collision is simply given by the mass of clay and its velocity. So I would write this as P naught x, and this is just little m dx, okay? And then, you know, thinking back to the sketch that we drew, we want to think about the final momentum of the system. And so the final momentum of the system, and you might be, let me just come back to this really quick. You might be like, well, you said the system, but we only wrote something down for the clay. But if we were to write something down for the box, it would just be this, right? And so this is just little m, little v sub x, right? So now let's look at the final momentum of the system. And this I would write just p sub x without the 0 in the subscript. I think you're probably all used to that by now. And I'm going to say, well, they're moving together as one now, right? With the same velocity. And so their mass is just the combined mass of the clay and the block. And now this is where I switch my notation. I call this big V because I have to keep it separate symbolically from the other velocity, right? So this is it. We've written out the initial momentum of the system and the final momentum of the system. And so we equate the initial momentum of the system to the final momentum of the system. And that could be written perhaps like this. And we have little m, little v sub x. Now this equals big M plus little m inside parentheses times big V sub x. And solving for big V, right, which is their shared speed, is just little m over big M plus little m times V sub x. Now, I think that I will actually, I didn't do this in my notes, but I think I will calculate the number here because we expect perhaps from sort of our everyday experience that the box is much more massive than the clay, and so we would expect that their combined or shared speed would be lower than that of the clay. So let me just do this on the other screen here. So 0.5 divided by 10 plus 0.5 times 10. Yeah, and I'm finding that it's pretty small. It's about 0.477 meters per second. Like so. And that I think sort of corresponds to what we would expect in real life. Okay, so that's an example of, what did we say? You know, it's really embarrassing, but I can never remember the names for these things, but that was, yeah, that was a perfectly inelastic collision, okay? I know how to do the physics, right? If you tell me, you know, kinetic energy is conserved or it's not or whatever, I know how to do that. I just don't remember the names. Okay, so here, let's look at this example. You notice that a car with mass big M equals 1,000 kilograms is left on the street idling in neutral. If you're feeling devious and want to throw a golf ball with mass of 0.05 kilograms at the bumper such that the car starts rolling down the street with speed v sub x equals 0.1 meters per second after the collision, with what minimum speed must the golf ball strike the car? Assume that the golf ball bounces back at half the speed after it hits the bumper. So let's also make a sketch of this and see what it looks like. So I'm gonna just bring up the other screen again. Okay, so what we have now initially is, and I'm just going to draw the car as a box. I'm not an artist. Like that. That's the car, right? Isn't it? Isn't it a nice car? And the golf ball is moving toward it with. I don't think I called it anything in the problem statement, so I'm going to call it this. I'm going to call it U. U initial in the x direction, the x component. And this has mass little m, and this car has mass big M. And notice that the car, I tried to make it clear in the sketch, but maybe it's not, but is not moving, right? It's just there. And so this could be perhaps what your sketch looks like. And then let's think about what happens finally, right? So essentially right after the golf ball is bounced off the bumper of the car, now the car is moving to the right with some, what did we say? We called it V sub x. And the golf ball is now moving to the left. And we said that it's it bounces back at half the speed, right? So let's say u sub x over 2, like that. And so this is you know, admittedly a pretty crappy sketch, but hopefully it gets the point across. This is what we're sort of thinking about. And so, and again, right, the sketch doesn't necessarily indicate this, but we're thinking about like just right before the golf ball hits the bumper of the car and right after it bounces off. And so again, if it helps, you could think like, well, what does this situation look like when the golf ball is just like millimeters away from the bumper? And let's go through and solve this. So it amounts to essentially the same process, right? Except this is going to be a little different because now, in this case, they're not moving together, but we can deal with that. It's totally fine. So the initial momentum in the x direction is simply due to the golf ball's motion. So we'll write this in the same sort of symbolization, if that's a word, like that, right? It's just the mass of the golf ball times its initial x component of velocity. And that's it. And then again, it would be the same thing, right? If we wanted to include the car, it's fine, but we would just write big M times 0. And so, of course, that term goes away, and it just works out to be this. Okay, now we look at the final momentum, and this is where we have to be careful, because momentum is a vector, and perhaps that hasn't been completely obvious based on any of the examples that we've done so far, because the last example, for instance, had both objects moving in the same direction after the collision, right? But in this example, the way that I would write this, because I know that the golf ball is now, let's say as I've drawn it, moving to the left, is I would write something like this. So now the car is moving to the right, and so its momentum is implicitly positive. We could even put a positive sign here, a plus sign there if we really wanted to, but I won't do that. But now the golf ball is moving to the left, and so this is how you would write the final momentum, or I should say this is how I would write the final momentum. I think that you don't have to assume the signs and it works out okay. But what I would say is that if you know the signs of the terms, like if you know the directions of say the velocity vectors based on the problem statement, then put those into the equations that you write with the appropriate plus or minus signs, right? And so then let's do this. I'm just going to make a substitution because we know that the final speed of the golf ball is half the initial speed, right? We're told that in the problem statement. So we could just call this u initial over 2. And also, you might be wondering, like, why am I using a u for velocity? I don't think it's actually that uncommon to write a velocity as a u or even a w, and I might actually have occasion to do that. And I just do it so my equations don't become so cluttered, and I have to, write like a bunch of subscripts or primes or anything like that. This is the simplest way I'm aware of to deal with the fact that in problems like these, we often have to keep track of 2 speeds or velocities. But you can write it, of course, however you want. And so, well, again, we equate the momenta, right? I should say equating the momenta. And we have P initial x equals P final in the x direction, and then we just substitute in what this is. So remember that we have this is our initial momentum, and this is our final momentum of the system. And when we go through and solve this equation for the initial speed, or the initial x component of the velocity that the golf ball must have, we find that it has to be, well, it works out to be this symbolically, 2 times big M times v sub x divided by 3 little m. And this is going to work out to be very large, right? Because, you would probably expect, based on your everyday experience, that you would have to throw a golf ball pretty darn fast at a car to get it moving. And so what I found numerically was that this worked out to be about 1,300 meters per second. So you couldn't do this, right? Well, I don't want to tell you what you can and can't do. But in all likelihood, your average person couldn't do this. This is pretty fast. I think it's probably around, like, what, 3,000 miles per hour or something like that. I don't know, but really fast anyway. So this actually couldn't happen. But I think that this was an interesting problem because we probably went into it expecting, like, well, hey, could this even work, or suspecting maybe that it wouldn't work. And for most people, you can't throw a golf ball this fast, right? Okay. So we're going to look at one more example here, and this is going to be a combination of momentum and energy, right? We haven't seen anything like that, and this is like kind of a two-dimensional problem. Well, not really. We don't have to use the idea of two-dimensional momentum in this, but we will get to that soon. So I'm going to make a sketch of what's happening here just so it's clear to everybody. Let me first read the problem statement, and this is what you would call a ballistic pendulum. So a bullet of mass little m equals 10 grams strikes a pendulum of mass big M equals 2 kilograms. The center of mass of the pendulum rises a vertical distance of h equals 12 centimeters. Assuming that the bullet remains embedded in the pendulum, calculate the bullet's initial speed. So what I want to do first is convert these to our base units, and 10 grams, well, you just divide that by 1,000 to get kilograms, right? So it should be 0.01. Let me just move the decimal place in my head here really quickly. Like I said, I'm bad at powers of 10. Yeah, it should be 0.01 kilograms. And converting centimeters to meters is a little easier. This would just be 0.12 meters, right? We just divide by 100. And if you're still not comfortable with this idea of converting units, I mean, it's not something that I really plan on emphasizing, but maybe just practice, just give that a try with the method we discussed previously. But now what I'll do is I'll make the sketch here. And what we would have is, we have kind of three separate things to think about. Let's see here. I'll call this like the zero subscript. And at this time, the pendulum is just hanging, and the bullet, let's say, is like right here. It's about to hit it. And remember, the bullet has mass little m, and we can probably safely just say that it has a velocity vector that points to the right. So let's do that. And I'll call this u again. I'll say, I don't know, u naught maybe. And it's like that. And the reason that it's probably safe to make this assumption that I just discussed is because to actually calculate the y component of the velocity for the bullet, we would need more information. So the problem statement doesn't even give us enough to calculate it. And you might be like, well, Ryan, just write a better problem. But I didn't write this. This is from the book, right? So you can't even blame me. And so, anyway, it's written by a professional, right? And so I think that the idea is, though, that as a bullet is going to move pretty fast, and we should find that its speed is very large. And what that means is that for, like a reasonably short distance, it's not going to fall very far in the y direction as it moves toward this pendulum, right? And that's what I'm going with, at least. Okay, so then what happens, right? Let's call it. Now we might not need to actually do three separate parts. Let me try it without. Okay, so then at 1, right, I'll indicate with a 1, or when I actually write this, there will be no subscript. Hopefully it's clear. But no, let me not. Let me just do this. So now the bullet is embedded in the pendulum, and this system has mass big M plus little m, right? And so this would be another example of a perfectly inelastic collision. And immediately after the bullet is fully embedded in the pendulum, this is going to have a velocity like this. Let's just call it big V. And then finally, what's going to happen is the pendulum is going to swing up, right? Maybe like so, with the bullet still inside. And when it reaches its maximum height, the kinetic energy is at a minimum, right? The kinetic energy is 0, and the gravitational potential energy is at a maximum. So remember that we said that it rises by an amount h, and so what we're saying is that we're going to define our y equals 0 to be here. So the pendulum bullet system immediately after the collision has 0 gravitational potential energy, and then it changes to have some non-zero value of gravitational potential energy, and when its gravitational potential energy is at a maximum, its kinetic energy is 0. So hopefully this helps the sketch here. So let's just start writing some stuff out and see what happens. It's never a bad idea, right? So the momentum of the system just before the bullet hits the pendulum is, and we'll call this P, and I'm going to drop the subscripts here at this point, because this is what I would do, and I think I did this like a bit when we were talking about one-dimensional kinematics, is that, you know, there's really no reason, if we just all agree we're talking about the x direction, to write subscripts. So this is just going to be mu naught, right? And this is the momentum of the system, like when the bullet is just very, very, very close to hitting the pendulum. Okay, so the momentum of the system, let's say immediately after the bullet is fully embedded in the pendulum, right? So the bullet has now come to a stop. Well, it's not moving relative to the pendulum now, right? It's in a fixed position inside the pendulum. And this is going to be, we said, P equals big M plus little m V. And so we can figure out, right, we can set the momenta equal to each other like this: P initial equals P final, and mu naught equals big M plus little m. And I think that I'll write a 1 here, just because that's what I said I would do, but most of the time I probably wouldn't like that. Oops, 1. There we go. And then this is 1. And in the sketch, though, I don't want to, I know I'm going back and forth here. I don't want to confuse anybody. So I'm just going to call that V, so I'm being perfectly consistent with the sketch that I made. And this is V also, right? Okay, so we can solve for, from this we can solve for therefore, what V must be. V must be, and this is pretty similar to what we found with the clay and the block, it just must be mu naught over big M plus little m, right? And now we use this we use this to calculate the kinetic energy of the bullet and pendulum together after the bullet is fully embedded in the pendulum. And so what we find is that the kinetic energy here, I'll call it K1, I suppose, is 1/2 big M plus little m v squared, right? So this is 1/2 big M plus little m, and I'll probably make Mathematica do the algebra here at this point. Like this. Although actually I don't think I need to, because we see, I think, that a factor of the sum of the masses cancels, right? And it looks like it should just be, I'll double check this, I guess, because I don't want to do bad algebra. But it's looking like it should just be m squared u naught squared over 2 times big M plus little m, right? I shouldn't have to check this, but I'm going to, so just stand by. Yeah, it is that. Okay, cool. And then we equate this, right, from conservation of energy to the gravitational potential energy. So equating this to the gravitational potential energy, we would write K1 equals U2, and symbolically it's just this. This is what we found for K1, and U2 will be big M plus little m g h, right? And we want to solve this for U, or U naught, I should say, because that's what we were originally asked about, right? In case you forgot, I know I almost did, so understandable. So I'm going to make Mathematica do the algebra for me. We have big M plus little m times g times h. We want this for U. And I am finding this. I am finding that the speed that the bullet must have been traveling at is the square root of 2gh, and then here we have big M plus little m over m. And this is what Mathematica gives me after fully simplifying things. Though it is weird that if we feel like we should have a factor of the sum of the masses squared. Well, I'm sure it's okay. I mean, Mathematica doesn't make mistakes, right? And I put it in fine as far as I can tell. So this is what we would get. And let's calculate this, because that will, we probably expect this to be like several hundred meters per second or something like that, right? Because it should be pretty fast. So we said, well, G is 9.81, of course. H is 0.12, M was 0.01, and big M was 2, right? 2 kilograms. Yeah, cool. This all looks good. Okay, so let's see what number we get here. Yeah, and Mathematica is telling me that this is about 308 meters per second, which is, it seems reasonable, right? 8 meters per second. and this is about 1,000 feet per second, right? Which might be a little more understandable for us Americans. I know we're not all Americans, but some of us are, right? So, well, maybe we are all Americans. I don't know. But it's this, uh, 308 meters per second, and that seems pretty reasonable. Let me stop rambling here. Okay, so that's that, and that's the conclusion of this video. I will put one out tomorrow where I just work some examples, so keep an eye out for that. I almost hate to say this, but I think that at this point you all should probably just subscribe to my channel, because that way I won't have to email you every time I post a video, and you'll just know. So if you don't mind doing that, please do. I guess I can continue to email people if I don't see that I'm getting any subscriptions, right? But anyway, I will see you in the next video.